1930. America is racing into the sky. A new skyscraper rises every single month. But hidden inside every steel frame is a mathematical nightmare: static indeterminacy. Every joint relies on every other joint, and what is the only way out? Solve a massive matrix of simultaneous equations by hand. Weeks of brutal arithmetic, one minor slip. You throw it out and start from scratch. Hardy Cross was a quiet professor from Illinois who turned structural analysis upside down. In 1930, he published a paper just 10 pages long, 10 pages that would dictate structural design for the next 40 years. His concept was brilliantly simple: freeze the structure, clamp every joint completely rigid. Load it up, each clamp locks in an unbalanced moment. Now, release just one joint. Its moment splits between connected members, and half of each share travels next door. Clamp, release, distribute, repeat. With every cycle, the unbalanced moments vanish. The frame quietly relaxes into total equilibrium. No computers required. Just simple, elegant iteration. But that was how the world built its buildings for the next 40 years. Today, finite element solvers handle the linear algebra in milliseconds. But Hardy Cross gave engineers intuition. He taught us to visualize how moments actually flow. This is the moment distribution method. Suppose we have a beam with the load configuration shown on the screen. Statics gives us 3 equations. This beam has 5 unknown reactions. It's statically indeterminate. Equilibrium alone cannot crack it. We need a routine. Here's the trick. Clamp every joint so that nothing is allowed to rotate. Now release just one joint. It spins until the moments on either side of it balance, and then we clamp it again. Every release leaves a smaller error behind than the one before it, so we repeat until the corrections become too small to matter. That is the entire method. Step 1. With every joint clamped, each span behaves as a beam fixed at both ends. Standard tables give us the clamping moments. Step 2. When a joint is allowed to let go, which member takes the moment? Rotate a member end, and it fights back. That resistance is its stiffness. K equals 4 EI over L. Short, stocky members fight hardest and take more. Our 2 spans are twins. Same length, same EI. So their stiffnesses are equal. Each member takes its share of the total stiffness at the joint. That share is the distribution factor, K over the sum of K. Step 3. Rotate the near end of a member, and the far clamped end feels it too. Exactly half of the applied moment travels across the span, with the same sign. That is the carryover factor, 1/2. Step 4. Set up the bookkeeping. 1 column for every member end. Write in the distribution factors along the top, then the fixed end moments underneath. Everything from here is arithmetic. Step 5. Start with the worst offender. Joint C, C, is a simple support. There's nothing there to resist a moment, so its final value has to be 0. Right now it holds plus 80, so we add minus 80 to balance it. All of it, since the distribution factor is 1. Then carry half of that across to B, minus 40. And we clamp C again. Now release joint B. Add up everything that joint is holding. Plus 64, minus 80, minus 40. That's minus 56 kilonewton meters out of balance. Distribute the opposite. Plus 56, using the distribution factors. Plus 28 to NBA, plus 28 to NBC. Then carry half of each outward, plus 14 to A, and plus 14 to C. Step 6. That carryover just unbalanced joint C again. So release it, balance it, carry over. And go back to B. Watch the numbers shrink. Each cycle is roughly a quarter of the one before it. 80, 56, 14, 7, 3.5. The beam is converging on its answer. Step 7. Sum every column, top to bottom. Joint B, plus 95.9 on one side, minus 95.9 on the other. Perfectly balanced. Joint C, 0, exactly as required. Step 8. Hang the bending moment diagram on those three values. And that's the whole method. One loop you can run on paper. Clamp every joint and write the fixed end moments. Get the stiffnesses. And from them, the distribution factors. Release a joint, distribute the unbalance. Carry half to the far end. Repeat until the corrections vanish. Sum the columns and draw the diagram. Hardy-Cross turned structural analysis into arithmetic.